Hello guys, welcome to our new video series, and it's a continuation series of Trie Data Structure. As you know, we had previous videos about how we implement the Trie Data Structure in our code, and this is the continuation series. So I'm just gonna give you guys the summary of Trie Data Structure again. So what is Trie Data Structure? It's a prefix tree. It's like a tree like data structure, same like binary tree, another black and red black tree. So it's basically used for store strings efficiently by prefixes. Okay, so common prefixes share the same path, useful for fast search, which is O of one, autocomplete, and dictionary lookups. Okay, so it seems like a hash map, like hash map also have O of one. So example of try. So this is a good example of try data structure, which is you see we have a root node which is empty right now, and which stores their child address. So if someone's wants to insert are in English word, so it's gonna create a new node. If it's not exist, it will create a new node a, and then it will create a new child for a, which is r, and then create a new node which is e. So for example, if and nothing is here, it's gonna create a new node a r e. Okay, so and in case if someone's enter, like someone wants to insert a new word which is ant, a and t, so it will not create a again. Okay, so it will go to a and then make a new node n and then t, and make sure for every word, like once the word end, you need to mark the word true or false. Okay, true means the string is valid, and false means string is not valid. Okay, so for every word at the end you see the color red, which shows that the string is complete and the word is valid. So now this structure stores several words, which is r, s, dot, okay, do also a word, and then new, and then not, and no. So it has, but it's using the same prefix for different strings. Okay, if you want to go to more detail, you can see my previous video, and in this video we will just discuss about the summary of triad data structure and then go deep into the triad data structure. Okay, so as you know, these are try operations, which is insert, which is o of l, which is of length, for example, o of 1, and then search, prefix search, it has the same of l. Okay, it's efficient for dictionaries and autocomplete. So in real world examples, these are the autocomplete in search engines. You see, when you type google, you just type um, uh, face, and it will show you all the words related to face, facebook, face snap, face cam, whatever word came from a face wash, whatever word came from face, it will show. So how it's gonna be show? By using you they use basically the try data structure at the back end, so that can shows, maybe they can use a different one, but as you know, you can use the same thing by using the try data structure. That shows all the autocomplete. you know that's a real very good use case for try. And also for spell checker as well. If you want to make a spell checker, you can do, for example, someone's, when you type anything on the google and the spelling is incorrect, it shows the suggestion that you are trying to enter this word or another word. Okay, and also networking, routing as well, and large dictionary storage. So we have the try efficient prefix, which is string based storage, and then we have radix tree, which is a type of try, but it's a compressed version of try. And then we have a patricia tree, which is optimized for space and routing. So now we'll discuss about what is the patricia and the other one, radix. So for the radix tree, which is basically another name of Patricia tree. Okay, so first we're gonna use the Patricia. So Patricia is a compressed version of a standard Trie tree. Okay, so for example, you know, edge labels can store strings for multiple characters, not just one characters. Okay, so you can store, like, the node can have multiple characters as well, not a single path. Okay, so you can see if it's reduced memory usage, collapsing chains of nodes with one child, still preserve the prefix property as well. Okay, so these are the pros and cons. Like, more space efficient than a regular tree, still use the same OFL, and then slightly, but cons are like it's slightly complex implementation than simply tree, and then insertion can be more complicated due to edge splitting as well. Okay, so you see, for example, we have a word to or t. So if you want to store t and ted and 10, so we can store. Notice the single child paths are compressed. Okay, like store as one edge if possible. Okay, so we can skip the letters as well. Okay, um, and then we have the radix tree, which is basically another name of Patricia tree. And then you will see it's compressed. It's same characteristics like compressed tree. And then edge labels can be string, not single characters. Okay, so the labels can be strings, full strings, not a single character. Okay, so you can string multiple strings as well. Okay, and then optimize for space. And then, yeah, so mostly they use dry data structure, but they can use the Patricia and radix tree as well. So I hope you guys understand what is dry data structure. So we're gonna in my next video we will show you how we implement try, and then all the other data structures as well. Thank you. Stay tuned for more informative videos.